Hello student friends. So in this video lecture we are going to discuss the various pressure and flow sensors mainly used in the embedded system or IoT based systems. So first we are going to discuss the various pressure sensors, and in the second part of this video we will see the various flow sensors. So part 1, so here we are going to see various pressure sensors. So first we will see the basic fundamentals related to the pressure sensor. So a pressure sensor is defined as the force per unit area and can be measured in PSI, that is pounds per square inch, or inch of water, or millimeters of mercury, or Pascal PA, or newtons per meter square, or measured in bar. So until the introduction of the SI units, the bar was quite common unit for the pressure measurement. So we can say that pressure is equal to force per area. In particular, the essential feature of the conventional pressure transducer is an elastic element which is mainly observed in all pressure sensor, which converts energy from pressure system under study to a displacement in the mechanical measuring system. So usually you will find the diaphragm or elastic element in the pressure sensor and the assembly to measure the mechanical displacement. An additional feature found in many pressure sensor is an electric element, semiconductor based electric element, which in turn or converts the displacement of mechanical system to an electrical signal. So these pressure transducer are mainly categorized into, that is, active transducer based pressure sensor and passive transducer based pressure sensor. So here in these two figures we can able to see the fluid energy input applied to the elastic element which is observed in the pressure transducer, which is the active transducer which produce the mechanical energy in the output form. And the second category, so here you will find the elastic element plus electric element in the assembly of the pressure transducer. Again in this case you will find the input, that is fluid energy, to the passive transducer, and output other mechanical or electrical energy output, which is again connected to the next stage of the machine or the circuit or the system. But in case of passive transducer, you will find the external electrical supply or auxiliary electrical input energy for the excitation of the electric part or the circuitry or the element available in the pressure transducer. So as we know very well that the pressure transducer, if they consider the passive transducer which requires external excitation voltage, okay, so this auxiliary electrical energy input required for the passive, that is impedance type of the material, which is mainly observed in the package of the passive transducer. But in case of active transducer, there is no need to apply the external electrical source as the input to the pressure transducer or active pressure transducer. Now we will move one by one towards the various pressure sensors. In that, first one is the mercury pressure sensor. So in this type of sensor you will find the mercury in the tube, which is mainly used to measure the resistance. So it's a simple yet efficient sensor, is based on the communicating vessel principle. Its prime use is for measurement of the gas pressure. So this particular mercury pressure sensor mainly preferred to measure the gas pressure. So here in this figure we can able to see a glass tube is there, and in the tube you will find the mercury, and also you will find the resistive element immersed or present in the mercury, and depending on the pressure applied at the one end of the tube, the mercury will move upward or downward depending on the pressure, and the two terminals of this resistive element which is available in the tube is connected to the differential amplifier, op-amp based differential amplifier. So depending on the movement of the mercury inside the tube, the change in the resistance, and according to that you will get the output from the amplifier. So a U-shaped wire is immersed into mercury which shorts its resistance in proportion with the height of the mercury in each column. The resistors are connected into Wheatstone bridge circuit that remains in balance as long as the differential pressure in the tube is 0. And when pressure is applied to one end of the tube or arm of the tube, the bridge get unbalanced. So this disbalances the bridge, which results in the output signal from the op-amp circuit. So here the higher pressure in the left side of the tube. So here in this diagram we can able to see one pipe is inserted or connected at the one end, where the gas pressure is applied through this particular pipe, and the gas will go inside this, and he will apply the pressure to the mercury, and mercury will move upward, and due to this reason the change in the resistance or the bridge get unbalanced, and according to that the change in the resistance and also the circuitry will provide the output voltage. So the higher the pressure in the left side of the tube, higher the resistance of the corresponding arm, and lower the resistance of the opposite arm. And this particular change in the resistance measured in delta R. So the output voltage is proportional to a difference in resistances delta R of the wire arm that are not shunted by the mercury. So we can write output voltage is equal to supplier voltage into delta R by R. Now we will move towards the next type of the pressure sensors, which are designed by using bellows, membranes and thin plates. So pressure sensors also contain deformable elements whose deformations or movement are measured and converted by displacement sensor into electrical signal representative of the pressure value. So these deformable or sensing element is the mechanical device that undergoes structural changes under strain resulting from pressure. So usually these kind of devices were burden tubes, C-shaped or twisted or helical type of structure, corrugated and catency diaphragms. Also you will find the capsule kind of structure, bellows, barrel tubes and other components whose shapes was changing under pressure. So in these two diagrams we can able to see the figure A shows the steel bellow for the pressure transducer, which is observed with the pressure sensors or pressure transducer, and figure B shows the typical arrangement which consists of metal corrugated diaphragm. So here we can able to see the corrugated diaphragm is placed or fixed inside the arrangement, and the central part of the diaphragm is connected one stud or the rod, and this particular rod is again connected, or this particular rod will apply the pressure to the strain gauge which is located at the bottom. So depending on the applied pressure P from the top or bellows, the pressure will apply on the diaphragm, and diaphragm will move upward and downward, and as I said, the central rod is attached to the diaphragm and also it is attached to the strain gauge. So due to the movement of this particular rod, the strain and its value get changed, and with respect to that we are getting the change in the output voltage from the driver circuitry or the preamplifier or the amplifier circuitry. So bellows is used for the conversion of pressure into linear displacement, which can be measured by an appropriate sensor as shown in figure B. Thus bellows perform first step in the complex conversion of pressure into electrical signal. The bellows is characterized by relatively large surface area and therefore by large displacement at low pressure. The hardness or stiffness of the seamless metallic bellows is proportional to the Young's module of the material and inversely proportional to the outside diameter and to the number of convolutions of the bellows. So the stiffness also increases with roughly the third power of the wall thickness. So depending on the design or the requirement for the particular application, you will find the various thickness and dimensions of the bellows. So a popular example of pressure conversion into linear deflection is a diaphragm in an aneroid barometer. So a deflecting device always forms at least one wall of pressure chamber and is coupled to strain sensor or strain gauge. For instance, strain gauge, like as we discussed in previous figure, which converts deflection into the electrical signal by means of piezoresistivity principle. So the latest pressure sensors are fabricated with silicon material or silicon membranes by using the micro machining technology. So in these two figures we can able to see figure A shows the thin plate with pressure P and Gmax in the normal condition, and figure B shows the thin plate under the pressure P with Gmax, which indicates the pressure is applied and the stress capital S. So a membrane is a thin diaphragm under the radial tension S, which is measured in Newton per meter. So the stiffness of the bending forces can be neglected, as the thickness of the membrane is much smaller when compared with its radius, at least 200 times smaller. So when pressure is applied to one side of the membrane, it shapes spherically like a soap bubble. That means after applying a pressure, the shape of the diaphragm or the membrane get changed. So at low pressure P, difference is across the membrane, and the center deflection measured with Gmax and stress with Smax are quasi-linear function of pressure. So we can write Gmax is equal to r square p by 4s, and sigma max nearly equal to s by g, where r is the membrane radius and g is the thickness. So the stress is generally uniform over the membrane area. The next category of the pressure sensor, which is based on the piezoresistive principle. So here you will find the plate or membrane having known area A and a detector that respond to the applied force are main components of this kind of pressure sensor. So here you will find a silicon diaphragm in the assembly of the pressure sensor, which consists of thin silicon diaphragm as an elastic material, and the piezoresistive gauge resistor made by diffusive impurities into the diaphragm. So a single crystal silicon superior elastic characteristics, where vertically no creep, no hysteresis occur even under strong static pressure. So here the gauge factor of the silicon is many times stronger than that of the thin metal conductor. So as far as the fabrication is concerned, it's specially fabricated strain gauge resistor connected as the Wheatstone bridge. So again you will find the driver circuit or the Wheatstone bridge kind of circuitry, which converts which is responsible to measure the change in the resistance and provide the sufficient resistance output or resistor to the next stage to measure the differential voltage. So the full scale output of on the order of several hundred millivolts, and due to this reason the main advantage of this particular sensor is that signal conditioner is required for the bringing the output to an acceptable format. So here the first figure shows the top view of this particular piezoresistive sensor, where y and x, these are the movement or the directions, and here you will find the R1 and R2 two resistances and the diaphragm. The second figure we can able to the side view of this particular sensor, where the silicon diaphragm is working depending on the pressure P applied from the top and the diffused resistance R1 and R2. So depending on the movement of the diaphragm, the variations in the resistance were responsible to produce differential output. The next type of the pressure sensor is the capacitive pressure sensor. So in this particular capacitive sensor you will find the diaphragm displacement, which modulates the capacitance with respect to the reference plate or back plate. So this conversion is specially effective for low pressure sensors. So an entire sensor can be fabricated from solid piece of silicon, thus maximizing its operational stability. So the diaphragm in this particular sensor can be designed to produce up to 25% capacitance change over the full range, which makes these sensors candidate for the direct digitization. So while designing this particular capacitor sensor and to achieve good linearity property, it is important to maintain the flatness of the diaphragm. So traditionally these sensors are linear only over the displacement that are much less than their thickness. So to achieve this linearity property or the linear range is to take the diaphragm with grooves or corrugations, and these corrugations can be achieved by using the micro machining technology. So here you will find the two kinds of capacitor sensor, that is a plain and corrugated diaphragm based pressure sensor. So the planar diaphragm are generally considered more sensitive than the corrugated diaphragm. Planar means there are no corrugations on the diaphragm. So these are more sensitive than the corrugated diaphragm with the same size and thickness of the diaphragm. So in this figure A shows the response for the corrugated and planar or flat diaphragm based pressure sensor, where the center displacement in micrometer versus applied pressure in inch for H2O. So this is for the corrugated, and the second response for the planar or flat diaphragm based sensor. And at the right hand side or in figure B, we can able to see the disassembly of this particular capacitor sensor. You will find one bellow and the inlet where the pressure can be applied to this particular inlet, and here you will find the two plates, top plate and bottom plate, and the device leads or the terminals where the driver circuitry is connected, and external housing for this particular mechanism. So here the bellows which is attached to the diaphragm. This diaphragm again will move the plate upward and downward, and depending on that we are getting the change in the capacitance to this particular device terminals. The next type of the pressure sensor, which is based on the optical principle, that is optoelectronic pressure sensor. So here the optical readout has several advantages over the other technologies that we have discussed. So here you will find the simple encapsulations, and one advantage, that is small temperature effect, high resolution, and the accuracy as comparing to the other or the sensor that we have discussed. So these kind of sensors especially promising are optoelectronic sensor operating with the light interference phenomena. So these kind of sensors use the Fabry-Perot FP Fabry-Perot principle for measuring the small displacement. So the simplified circuit we will see in the next slide. So in this diagram we can able to see at the bottom the assembly, which consists of the silicon diaphragm which is connected to the Fabry-Perot interferometer, also are attached to the pressure sensitive movable mirror, and on the top of this particular assembly you will find the glass, and this particular assembly is working with the light emitting diode and photodetector. So light emitting diode is responsible to generate the photonic energy. So this particular silicon diaphragm based assembly will detect the light energy or photonic energy from the LED, and the reflected light energy again given to the photodiodes. So here we can able to see the SiO2 and aluminum tips of this particular integrated Fabry-Perot filter, and the photodetector is responsible to detect the photonic energy. The leads of this particular photodiodes are connected to the driver circuitry to amplify the signal. The intensity of the reflected light energy to this particular towards this particular photodiode depending on the movement of the diaphragm. So here from bottom the pressure is applied to the through the inlet to the diaphragm, and this diaphragm will move upward and downward, and also the pressure resistive movable mirrors also move, or the FP Fabry-Perot interferometer will move upward and downward, and with respect to that the photodiode will receive minimum to maximum light energy, and depending on this photodiode will generate the output voltage. So depending on the light intensity, the photodiode will give you the change in the output voltage. So this particular assembly consists of the silicon diaphragm. This particular diaphragm will move, or the movement or the displacement of this diaphragm depending on the pressure, and with respective to the pressure the change in the light intensity or the light energy that he is receiving from the light emitting diode, and he will reflect the intensity of light towards this photodiode, and photodiode will change, or photodiode will give you the change in the output voltage. So this is the basic working principle behind this particular optical based